All right, greetings everyone. Welcome to the second part of the video for section 3.1. Continuing on, we've learned about power functions in the first part of the video, so we're going to take that a little step further in this next part. Okay, so we're going to look at what happens if we start combining power functions now. So before, on our last slide of our last video, we had these two power functions, negative 2x squared and 5x cubed. And what we might wonder is if we took them and added them together, so did negative 2x squared plus 5x cubed, which first of all, notice I cannot combine these two because they are not like terms. They have different powers of the variable. The question would be, what type of function is that now? The negative 2x squared plus 5x cubed. Good question, Cody. Well, it's what we call a polynomial, okay? And so a polynomial, you'll see here, they're written as f of x equals some a naught, which means some coefficient times a1 times x plus a2 times x squared, blah, 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 blah. So basically it's saying that if you added together a bunch of power functions, that's what makes a polynomial, okay? And in a polynomial, each of those little a things, a sub I things here, those are what are called coefficients. So those are basically the numbers that are next to the variables or by themselves. They can be positive, negative, or zero, and whole numbers, decimals, or fractions. A term of a polynomial is any one piece of the sum, that is a coefficient along with the power of x that it goes with, as well as the sign in front of that coefficient. The degree of the polynomial is the highest power we see in that polynomial. And the leading term is the term that contains that highest power. So notice there's two different things here. So the degree is the highest power. The leading term is the term that contains the highest power, okay? And the leading coefficient is the coefficient in that leading term, okay? All right, and one other thing I should say is that for something to be a polynomial, all of the powers in the polynomial have to be whole numbers. Okay, you can't have something like f of x equals 3x squared minus 7x to the 1/2. This is not a polynomial because of that x to the 1/2 power there. Okay. All right. So let's just do some practice with these terms. So here we're given two polynomials and we're asked to determine the number of terms, the degree, the leading term, and the leading coefficient. So for the first function, h of x, see that it's negative 3x to the fifth minus 3x squared and then plus 1. And notice how I underline each one of those little pieces there separately. So for the number of terms in this one, okay, that would be 3. The degree, again, is going to be the highest power we see. And in this case, notice the highest power is a 5. So the degree would be 5. The leading term, which I'm just going to write, well, yeah, I'll write leading term. Okay, again, that's the term that contains the highest power. So the answer here is not 5. The leading term would be negative 3x to the fifth, since that's this term here that contains the highest power. And then the leading coefficient, which is another important thing to identify, leading coefficient. Okay, well that is negative 3. So that's just the coefficient from that leading term, so the number in the front. So here, it's a negative 3. Okay. Let's do a similar analysis with the second one. So for the second polynomial down there, let's first figure out the number of terms. So I count 1, 2, 3 there. The degree, and again, remember the degree is the highest power we see of the variable. So in this case, that would be a 4. The leading term now is the term that contains that highest power. I want to be careful here. Sometimes folks think that the leading term is the first one. That is not true. Okay? The leading term is the one that contains the highest power. So that would be this term here, that 4x to the 4th. And the leading coefficient would be the coefficient in that term, which here is just the 4. Okay? So that would be our terms, number of terms, degree, leading term, and leading coefficient of that second polynomial. All right. Let's now talk about long-run behavior of polynomials. And so here we've been given 3. We're asked to graph them on our calculators and describe their long-run behavior. If we were in class together, we would do this. And so I'll just tell us what we would get for each of those. So for the first one, what we would get is that as x goes towards positive infinity, f of x also goes towards positive infinity. And then as x goes towards negative infinity here, we would get f of x going towards negative infinity. For the second one, what we would get, and I'll do this in blue, is that as x goes towards positive infinity, here we'd have f of x going towards negative infinity. And then as x goes towards negative infinity, here we would actually get that h of x, sorry, I wrote f of x, I meant h of x. We'd have that h of x is going towards positive infinity. And then finally, for this last one, we would have that as x goes towards positive infinity, k of x is going to go towards positive infinity. And then as x goes towards negative infinity, k of x is also going to go towards positive infinity. Okay, so we have these 3 sets of long-run behavior. Can we conclude anything or see if there's any clues inside the function itself that tells us how to figure this out? Well, notice for this first one, right, we had that as we went towards positive infinity, negative infinity towards negative infinity. If you think about what that would look like on a graph, it would be something like this, which kind of looks like the long-run behavior of an odd powered function, right? And when we look at this function, we see that it has an odd powered function there as part of it, so that's interesting. For the second one, we have that as x goes towards infinity, h of x goes towards negative infinity. So that one, it's going to look something like this. Whoops, that's terrible though. Something like that. And as x goes towards a negative infinity, we see it going up. So it looks like this. So it kind of looks like the one before, just reflected, right? If we compare this here to this here, see they're a similar shape. They've just been reflected over the horizontal axis, which makes us think that this one might also have some sort of an odd powered shape, which again, see there's an odd power there. Okay, interesting. And for the last one, we see that as x goes towards positive infinity, the k of x's go towards positive infinity. As x goes towards negative infinity, the k of x's still go towards infinity. So we get this shape, which kind of looks like the shape of an even-powered polynomial. And we see here that there is an even power. Okay, so it seems like the shape of the graph or the long-run behavior has something to do with the terms or some even or odds. And what do we notice about those specific terms that I highlighted in each case for each polynomial here? Yeah, notice that it was the leading term in each case, right? It was the term that contained the highest power, okay? And so that's is what determines the long-run behavior of a polynomial. All right, so the long-run behavior will match the long-run behavior of the leading term. So all we have to do to figure out what the long-run behavior is, and to also kind of get a idea of the shape of the graph, look at that leading term. All right, one more related to that. So here we're given a function h of x equals -2 times x minus 3 times x plus 4 times x minus 1 squared. They want us to figure out the long-run behavior, which means, as we just learned, we need to know the leading term. But to get the leading term here, we'd have to multiply this out, right? We'd have to FOIL the x minus 3 times x plus 4, multiply out the x minus 1 squared, and multiply those out. But that sounds like a lot of work, and particularly a lot of work we don't want to do. So is there a shortcut? Well, notice that another way to write this is -2 times x minus 3 times x plus 4 times x minus 1 times x minus 1. That's what the x minus 1 squared means. And if we think back to what we did in the prereq material, we know that if we multiplied all 4 of these things out, that what we would get as our highest power in this case is an x to the 4th. Okay, so it'd be x to the 4th plus a bunch of stuff being added, and that would be multiplied by -2. We would then distribute this -2 in, and our leading term would then be -2 x to the 4th, right? So it looks like we could figure out the long-term run behavior here by just looking at this -2 x to the 4th, which again we can get from the fact that here we had basically 4 things being multiplied, or we know that the highest power we'd get out of those is x to the 4th, and then there's also this -2 out front. So what that tells us is, well, this is an even power. So normally the graph would look like this. But that 2 in the front is negative, which is then going to reflect it. So make it go down like this. And from that, we can now get the long-run behavior. All right, so we can see from the shape there that as x goes towards infinity, positive infinity, the outputs, well, they're going down. So that would be going towards negative infinity. And then as the inputs there go towards negative infinity, so going the other way, like that, we also see that the outputs, the h of x's, are going towards negative infinity. Okay, so that would be our answer there. So this polynomial would have the long-run behavior of a reflected, even-powered power function. All right, thank you guys for watching. That's all for now.